Hello again. After a ton of technical difficulties following finishing the first page of Midterm 1, I am now ready to start the second page of Midterm 1. Okay, so 2A asks you to draw the intermediates of this mechanism, and you have to draw curved arrows to get to each step. So first, we're just going to draw the structure that'll result from the curved arrows that are drawn here. So just from these two curved arrows that we were given. So we're going to start drawing, just copying exactly what's there. Okay, let's just copy what's there exactly first, and then we can see how it changes. So now this OH group is attacking right there at that carbon. That's what this arrow is doing. And then at the same time, the two electrons in the pi bond are moving into the p orbital of that oxygen. So this oxygen now has 6 electrons and the 1 bond, so it's going to have a negative charge. Nothing else changes in charge because this carbon is still making 4 bonds right here, because it went from making 1 pi bond and 3 sigma to 4 sigma bonds. So that is the only charge. And yeah, and then that also shows that it's balanced because we can double check. There's a negative right here, and the charges should remain the same. So since there's a negative in the starting step, there should also be 1 negative charge over here. Okay, so the next step is the leaving group leaves. That's what it says right here. What's the leaving group? You know, there's like a whole bunch of things in this molecule that could be leaving. So we're going to look at the very last step and see what's going on. So we see that there's this main part of the molecule, and then there's also this group. And that looks a lot like this group right here. It has the R and it has the oxygen with the methyl between. And so we're going to assume that that's the leaving group. So in order for that to happen in this step, the leaving group will leave. Let's do that in black. So the leaving group is going to leave. But we see that there's 2 extra electrons on this oxygen. And when this leaving group leaves, that would leave a plus charge on this carbon right here. So when it leaves, we would be left with a carbocation, which isn't too bad because this isn't the worst kind of carbocation. We haven't gotten to this part yet in the class, so I won't go over that that's a tertiary carbocation. But we know that we had this resonance over here where the lone pair went onto the oxygen, so we can actually at the same time move this lone pair back here between the carbon and the oxygen. That way we're not left with the carbocation. So at the same time that the leaving group leaves, we're also going to draw resonance to make it better. So let's copy down the material. We've got the R prime, or R1, and we've got this pi bond here, this carbon, the OH, and now we have a double bond here with the oxygen, and we have our leaving group, which is this O, carbon, and then R, and this leaving group is going to have a negative charge on it because the 2 electrons that were right here between the carbon and the oxygen moved onto the oxygen. So now it has 3 lone pairs and 1 bond. So that's going to be a negative formal charge. And so then it says that there is a proton transfer. So actually we are going to erase this hydrogen that's on the carboxylic acid and draw in with a bond because we see that in the ending material, the hydrogen that's right there is gone, and there's now a hydrogen on the leaving group. So what we're going to do is we're just going to move that over. So the oxygen is going to take these electrons that are in the bond between the oxygen and the hydrogen, and they're going to go onto the oxygen, which is why the oxygen has a negative charge at the end. And then this oxygen right here in the leaving group is going to go ahead and take that hydrogen right there. And so that leaves us with the ending materials that we have right here. and that also is what the description says for step C. So moving on to the next step, or next question. It says circle and label R and R prime, two parts of the structure, below to show how it corresponds to the starting material. And we have to watch out and make sure that we know which atoms it starts and ends with. So we're going to look for just this group right here, because that's the starting material, not including this arrow for the what's attaching with the OH, just looking at that. And so we can see that same thing right here. Okay, so we're not going to include where the R prime was or where the R was. Oh, wait, we gotta include the carbon that's next to the oxygen though. Gotta watch out for that. So that means that over here, this carbon is gonna be here. And so this is what would have been R, and this right here is what would have been R prime. So it actually says to circle and label the R and R prime, not the rest of the material. So we're going to erase these circles because that's not what we're supposed to label. That was just to make things easier. It's easy to find that part, or easier to find that part than to find the R and the R prime right away. So let's see. So we want to find the material. So this is the ether, and then we have the carbon next to the ether. That's all part of the regular part of the molecule, or the main part of the molecule. And then it's next to that carbon that the R starts. So starting with this carbon right here. So this entire group is going to be our R. Let's erase this carbon so that it doesn't look like we're labeling just that one carbon as R, because it's this entire group starting with that carbon. Okay, and then where does R prime start? So we have the alkene right here up in our starting material. Then we have a methyl group, and then we have another carbon, and then our R prime. So we're gonna look down at number B, or letter B, and we see that the ether group, that was what I had circled, the alkene, the methyl group, the one carbon, and then this is where the R prime is going to start with the epoxide. That's what this is, the epoxide. So that's what starts our R prime. This is the first atom for our R prime, but the entire thing that I circled right there, that is our R prime. Let's make that a little bit bigger. Okay, so we've labeled R and R prime, and we can double check with our structure and just make sure that that's where it starts. You just have to really, really make sure, because you could include like this carbon or something, and then you'd be wrong because that's part of the main part of the molecule, not the R prime substituent. Okay, so this next part says, write a systematic name for the neutral product of the reaction above. So we're just looking at this molecule right here, and we're coming up with a name. So there's two functional groups besides just the main alkane chain. There's the carboxylic acid, and there's the alcohol. So we have to figure out which one has higher priority, because when we're naming an alcohol, normally, if alcohol is the biggest priority, we would name the alkane group. Well, first we name any substituents, then we name substituents. I think that's with an E, not an A. And then the alkane chain, and then we would have the OL ending. That's with the alcohol. But when we're naming a carboxylic acid, we have the substituents, then we have the alkane chain, and then we end with oic acid. And so in this case, the carboxylic acid takes precedent because it's a little bit higher priority than the OH. And so we have to still find a way to indicate that there is an OH group without ending with OL. And so that's when we call OH a hydroxyl group instead of just putting an OL at the end. So let's start with the end. It might make it easier. Oic acid. That's going to be the ending name. Okay, so now we have to count how many carbons are on the chain. Okay, so we got 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got 9. So that's going to be nonane, I think. Okay, so that's going to be, it would be nonane or nonane, however you say that. But we're going to change the ending to be oic acid, so it's going to be nonanoic acid. So nonanoic acid would just be this. 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the OH. That is nonanoic acid. 1, 2, 3, 4, 5, 6, 7, 8, 9. But we have an OH group on the end. So you might be tempted to name this 1 hydroxy or hydroxyl nonanoic acid. But that's not going to be the name because we start the carbon chain with the carbon that is in the carbonyl group or part of the carboxylic acid. So we actually have to call this one number 1, 2, 3, 4, 5, 6, 7, 8, 9. So the OH is attached to number 9. So it's going to be 9 hydroxyl nonanoic acid. Let's just make that all one color. Let's double check the key. Oh, it's hydroxy nonanoic acid. That's my bad. Hydroxy, we're just going to make a big Y. Hydroxy nonanoic acid. You can comment below in the YouTube comments if you want with how I should have pronounced that or try to sound it out. But yeah, you guys get the idea. Okay, so for the next part, it says to name the new functional group and state which reaction step, A, B, or C, would be the first step, that's important, that would not work. Okay, so we actually are going to be looking at the 2A again, at this mechanism, and we're going to look at B. Well, I guess we can look at A for the structure, but it might be easier to look at B to see what is changing here. And so, we can double check each part of the molecule, see what's different between these two structures. And so the first thing that's different is instead of having an oxygen right here, we have a carbon. So what does that mean? Instead of having the ester that we have up here in the mupirocin, we have just this carboxyl group. And so what is that called? That is called a ketone. That is the name of that functional group that we replace the ester with. Okay, so let's just look at the other one and see what functional group we replaced. So if we're looking at this again, this ester, we can see over here that instead of having the carboxyl group, we just have the oxygen attached to the two R groups, and so that is called an ether. So that is the name of the new functional group instead of an ester. You can double check that the rest of the molecule is the same. We're not looking at stereochemistry or anything over here, so it doesn't matter that those are looped around or kind of circular shaped, I guess, instead of in a straight line. we're just looking at the connectivity, and you can see that the rest of the molecule is the same. So now it's asking for both of these, which mechanism step is prevented by having, in this one, the ketone, and in this one, the ether instead of the ester. So we're going to look back at part A, and we see that step A is where we attack with the OH and we move electrons from the carboxyl onto the oxygen. So are we able to do that with this molecule? Yes, because we could add an OH right here, and we could move the electrons onto the oxygen. So step A is not prevented. That is not the answer right here. Then let's look at part B, or step B. Step B is where the oxygen that is attached to the carbon and the R group leaves. The leaving group leaves for step B. And so if we look down at here, we would need to have an oxygen right here to leave. And so we can't do step B because there's nothing there. The leaving group isn't the same. We would maybe have a different leaving group, but that is not what the mechanism above had. And so it would be step B in the mechanism that is prevented by having this structure instead of the ester. So we're going to do the same thing with this problem right here with the ether instead. And so starting again from the beginning, the OH is supposed to attack where the carboxyl is, and then the electrons are supposed to move from the pi bond to the oxygen. But here we don't even have a carboxyl to do that with. Yeah, so we can't even do step A in this case because this is an ether instead of a ester. So it is step A that is prevented. So that's page 2 of midterm 1.